Hey everyone, today we're looking at the section 4.4 notes. We're going to take a look at how to take the derivatives of exponential function and log function. So in order to get started for this y equals e to the x, if I want to take the derivative of this equation, I'm going to use that formal definition of the derivative that I did in chapter 2. So that's when we take our 2 points, take the point x, plug that in, you get e to the x. You plug x plus h in, and you get e to the x plus h. And then you do y2 minus y1 over x2 minus x1. So we wind up with this. We want those points to get really close to each other, so we take the limit as h approaches 0 of this. Okay, so then, again, if you want, you can plug in 0 for h. If you do that, you get e to the x minus e to the x. It's 0 over 0, indeterminate form, more work to do. So what's our more work here? Well, let's see if we can do a little factoring here. I'm going to rewrite this e to the x plus h as e to the x times e to the h, because same base, you would add your exponent. So I'm just doing that backwards. Those two are the same thing. Cool. And then what I'm going to do next is I'm going to factor out an e to the x. So when I do that, I get e to the h minus 1 that's left over out of those two terms. Okay, and I'm still taking the limit as h approaches 0. And then I'm going to use that limit rule where I can take the limit of all the individual pieces, so including this one. So it would be like limit as h approaches 0 of e to the x times limit as h approaches 0 of e to the h minus 1 over h. Just those two separate pieces. You can do it in any way you want. But I'm going to look at this chunk and this chunk. This here, if you plug in 0 for h into e to the x, there is no h. So that's just e to the x. So that's just e to the x by itself. And then for this piece here, let's do that on our calculator. So if I graph e to the x minus 1 over x and find out what's happening when x approaches 0, that would answer the same question. So here's this function, e to the x minus 1 over x. There's a little look at the graph, whatever the heck that is. It looks like it's approaching a value of 1. If we set up our table to start at 0 and count by something small, and then go back to the table, there is that error still, because I get that 0 over 0. And I still get 0 over 0, so I'd get e to the 0, which is 1 minus 1, 0 over 0. But I'm noticing that as x approaches 0, this thing is approaching 1. So that's how we're going to determine the limit value here using the calculator. So this whole thing equals 1. So that means that the derivative is e to the x times 1, or just e to the x. And that's kind of crazy. What that means is the derivative of e to the x is itself of e to the x. And we kind of did that a little bit going back to when we did graph sketches, right when we started all this stuff. So here was that sketch of e to the x. And if you notice, if you're trying to make a sketch of what the derivative would look like, if you notice, like, this thing is always increasing. So the derivative is always going to be positive. And then if you draw little tangent lines here, it's not going to be that steep. So the derivative is not going to be that big. But then it gets steeper and steeper and steeper. So the derivative value is going to get bigger and bigger and bigger. So this general structure, when we were drawing in the derivative, was looking something similar. We were doing like, oh, wouldn't it look something like that or something? Drawing in those tangent lines. And yeah, so now we're formally just proved that the derivative of e to the x is e to the x. And what we can do is we can just chain rule it out if there's something stuck on the inside. So say there's a function up there. So let's say e to the u. The derivative of e to the u is itself times the derivative of the exponent. So let's look at some examples of that. So here's y equals e to the 5x. So the derivative of e to the 5x is itself times derivative of the exponent. The derivative of 5x is just 5. For this one here, e to the x squared. The derivative of e to the x squared is itself times the derivative of the exponent, 2x. The derivative of 5e to the sine x. Now we're just getting crazy. 5e to the sine x, I'm just going to leave that 5 stuck on it right there. So the derivative of this is itself times the derivative of the exponent. The derivative of sine is cosine. And you're done. Okay, so that's just e to the x. How do you do the derivative for like 2 to the x and 5 to the x? Is it still the same thing? Well, there's a slight difference with those. So that's what we're going to call this a to the x, where a stands for any other number, 2 to the x, 5 to the x, all those other exponential functions, okay? Well, I'm going to use some little rules here. So we're going back, that's why we're practicing all those exponential and log rules. Because what I'm going to say is if you're taking the derivative of a to the x, that's the same as taking the derivative of e to the x times natural log of a. You're thinking like, how in the world are these two things the same thing? Well, here's our rules here. So I'm going to start with this thing here. And I'm going to use that exponents raised to exponents rule. You multiply them. So e to the natural log of a raised to the x would be e to the x natural log of a, seeing that those are the same. And then check this out. What I can do from there, so that's equal to this. And then with this e to the natural log of a, that's e to the log base e of a. So there's that rule where e to the log base e of a is equal to a. So all of this is actually equal to that a value. So something to keep in mind there. I'm using those log rules. And if you forget, like, why in the world does e to the log base ea, like, what does that equal? What are you even saying right now? How does that equal something? Well, we can kind of prove that. So check this out. This is written in exponential form because it's something raised to something is equal to something I don't know. If I rewrite this thing in log form, I would write log, and then this is the base, so this goes here. And then I'll write question mark here. And don't forget the log, when you're writing log form, the log is always equal to the exponent. So I'm going to rewrite this whole thing. The log is always equal to the exponent when you're writing in log form. So that whole thing, if you look at this form, I'm wondering what all of this is equal to. Well, check this out. Look what question mark is. Question mark is this a here. Everything else is matched up. So this e to the log base e of a is actually equal to a to the x. And the whole point of that is like, well, if I want to do the derivative of a to the x, that's the same as doing the derivative of e to the x times natural log of a, where x times natural log of a is just a number. So that's just going to be a number stuck. It might as well be e to the 5x, just like this one. E to the 5x is e to the 5x times 5. We can treat that natural log of a as just a number. So then the derivative of this is itself times the derivative of the exponent. So the derivative of this exponent, a number times x, is just that number. So here's the derivative of a to the x. It's all of this. And what we can do is resub a to the x for this ex ln of a right here. That was just a to the x times natural log of a. So here's how we do it. It's like the derivative of e to the u is itself, the derivative of e to the x is itself times the derivative of the exponent. Or in general, for all exponential functions, the derivative of a to the u is itself times natural log of the base times the derivative of the exponent. And you can even look at these for like e to the x. If you looked at e to the x, you can, okay, I want to take the derivative of e to the x. You can say it's itself times natural log of the base, natural log of the base times the derivative of the exponent. And if we remember what's natural log of e, e to the what equals e, this is also equal to 1. So this would be e to the x times 1 times 1. So the derivative of e to the x is e to the x. But in general, and that's just because natural log of e is 1, but that's not true for any other number. So the derivative of a to the u is itself times natural log of the base times the derivative of the exponent. So let's see how that works. That's just something to memorize, make your flashcard. Let's get these down. So here we have y equals 5 to the x. The derivative of 5 to the x is itself times natural log of the base times the derivative of the exponent. The derivative of x is just 1. So 5x times natural log of 5. The derivative of 2 raised to the x cubed. The derivative of that is itself times natural log of the base times the derivative of the exponent. The derivative of x cubed is 3x squared. Let's look at this one. 10 raised to something. The derivative of this exponential function is itself times natural log of the base times the derivative of the exponent. The derivative of tangent is secant squared. So it's cool. So now we can do any exponential function with any chain rule. Look at all these like crazy functions we're already starting to do. So the derivative of e to the u is itself times the derivative of the exponent. The derivative of a to the u, any other number besides e, is itself times natural log of the base times the derivative of the exponent if we chain rolled it out. Okay. So here's just some applications here. Find the equation of the normal line to the graph of this crazy x e to the x, whatever graph that is, at the origin. So the point's 0, 0. Cool. And first thing if I want a normal line, the first thing I'm going to do is find the slope of the tangent line at that point. And then, because that's what derivative is, slope of the tangent line. And then the normal line is just going to be perpendicular to the tangent line. So if I want to take a derivative of x e to the x, I'm thinking that's a product rule. So I'm going to take the derivative of the first times the second plus the first times the derivative of the second. The derivative of x is 1, so this is 1 e to the x, or just e to the x, and then plus x times the derivative of e to the x is itself, e to the x. Here's my derivative. If I plugged in 0, 0, e to the 0 is 1, plus x, that's a 0, and then e to 0 is 1, so this is equal to 1. That's the slope of the tangent line at the point 0, 0. If you want the slope of the normal line, just do the opposite reciprocal of 1 to get negative 1. So I have my point 0, 0, I have my slope negative 1, y minus 0 is equal to negative 1, x minus 0, which just simplifies to y equals negative x. Here's this curve here, there's x e to the x. That one I wouldn't expect you to know, just do it on the calculator. But then here's this normal line coming in that's perpendicular to that graph at that point. Okay, so that's exponentials. Now let's do logs. Let's see if we can figure this out. So don't forget that the inverse of an exponential function is the log function. So when you see something like y equals natural log of x, which is y equals log base e of x, these two things say the same thing. And if you just rewrite the form, you get e to the y equals x. So this, and this all say the same exact thing. And then we're seeing that this is the inverse of y equals e to the x equals e to the y. So we're seeing that logs and exponentials are inverse of each other. So if I'm looking at this here, I would like to take the derivative in this form and use that implicit differentiation to finish this one off. So I'm going to take the derivative of both sides. And so first I'm going to do the derivative of e to the y is itself times the derivative of the exponent. The derivative of y is y prime. And then the other side, the derivative of x is 1. So I created my derivative equation. Then I can just divide both sides by e to the y to get y prime equals 1 over e to the y. And I can leave my derivative just like this, or check this out, x is equal to e to the y. So that means the derivative of natural log of x is just 1 over x. Isn't that interesting? The derivative of natural log of x is 1 over x. And then you can just chain rule that out. The derivative of natural log of something is 1 over something times the derivative of that something. If the derivative of natural log of x is 1 over x, then the derivative of natural log of something is 1 over something times the derivative of that something. So let's look at some examples of that. Natural log of 5x, the derivative is 1 over 5x times the derivative of that, which is 5. And that would actually simplify back down to 1 over x. Let's check this here. Natural log of x to the fourth now. So the derivative is 1 over x to the 4 times the derivative of that, which is 4x cubed. If you simplify that, keep the 4 on top, 3 of these x's will cancel out, leaving you with 4 over x. What about natural log of square root of x? Not product rule because it's natural log of. That square root of x is inside. That's a chain rule. So this derivative is 1 over square root of x times the derivative of square root of x. And the derivative of square root of x is 1/2 x to the negative 1/2. You know, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And then if you flip this down, so here's some pre-calc. Going to look at the rest of this pre-calc here. So this is 1 over root x times, I can flip this down. X to the negative 1/2 is 1 over square root of x. So if you notice here, I got root x times root x is just x with a 2. So again, you can leave it just like this, but I just wanted to practice a little of that pre-calc with you, just to kind of keep that going. Okay, so what about every other log? If that's how you do the derivative of natural log of x, what about some other base? What about log base 10, log base 2, log base any generic a? Well, check this out. What you can do is that rule, if you guys remember the change of base rule, and the change of base is you can change any log function to any new base you want. The old base goes in the basement. If you want to, I'm going to change this to natural log. So natural log of x over natural log of a. And I don't know if you guys remember this change of base stuff. It was like, you know, when you did log base 2 of 8, you can rewrite that as natural log of 8 over natural log of 2. Let me write this too. 2. You can do any new base you want. These are divided. So you can do log of 8 over log of 2. The idea is you can change the base to any new thing you want. So I want to change my base to natural log because I just did the derivative of natural log that's just 1 over, 1 over x. So that's a good one to have. So let's do that. So let's change this log of any number base x to natural log of x divided by the natural log of that base. If you notice, this here is just a number now. So I'm not thinking quotient rule. I'm thinking there's a number that's multiplied by natural log of x. So I can move that number in front to get it as 1 over natural log of a. That's just a constant. That's a number. So I don't have to worry about that. It's just a number stuck to the derivative. So the derivative of log base a of x is going to be the derivative of this thing that I just manipulated. Then it's like, okay, a number times natural log of x. The derivative of natural log of x is 1 over x times the derivative of x, which is just 1, but 1 over x. So that means I have 1 over x times that natural log of a. So a number, natural log of a, times the x. And you can chain rule that out. What if you had a function on the inside? So that derivative is going to be 1 over u, instead of 1 over x, 1 over u times the natural log of a times the derivative of the exponent. So again, these are just, we definitely just have to memorize these just to kind of get used to these here. So let's take a look at a couple of these. So what if I have log base 2 of 5x? So that derivative is 1 over 5x, but then I got to add in that natural log of 2 base. And again, you can think of the natural log as the same way, because this would be natural log of e, which would be 1. So just be 5x times 1. But this one is 1 over 5x, 1 over u, 1 over 5x times natural log of 2, and then times the derivative of what's inside, times the derivative of u, which is 5. And let's see, that 5 and that 5 cancel out, leaving you with 1 over x times natural log of 2. Let's look at this one. Log base 3x squared. That derivative is going to be 1 over x squared times natural log of 3, because that base was natural log of 3, times the derivative of the exponent, which is 2x. This x will cancel out with one of those, leaving me with the 2 on top. One of the x's still left on the bottom, times natural log of 3. What about something like this? So this is kind of crazy, because in this case, this is the output is squared. This is we're squaring the input, log by 3x squared. This is squaring the entire output. So this is going to be chain rule. It's something squared. I don't know what's inside. So I bring the 2 down. Don't go inside. 2, all of this to the 1. Now times the derivative of this. So the derivative of log base 5 of x is 1 over x times the base, natural log of 5. 1 over x times natural log of 5 times the derivative of what's inside, times the derivative of u, which is the derivative of x is 1. Okay, so all of this stuff is the derivative. And if you notice, most of this stuff, it's just kind of like a number. There's a 2 here. You can kind of write this in any order you want. But if you bring it, you can write it all under one thing if you want. But I got a 2 on top. I got a log base 5x on top. And I got an x on the bottom and a natural log of 5 on the bottom. Feel free to write that any way you want. I'm going to put the x under here, so it's like a function. And then 2 over natural log of 5 is just a number. But just really write that any way you want. So kind of goofy, but again, these are just something that we'll make our flashcard for. We'll practice a couple and we should be good. So hopefully you had fun today, and we'll see you next time. Take care, everybody.